Hi, I'm Joe Snyders. I work for NTT Communications. And today I would like to share some insights in think we can architect robust routing policies relevant for internet operations. So I'm specifically not covering any data center side of this slide. It's just between peering partners and carriers. This is a collection of wisdom I gathered by emailing some of my colleagues and friends and asking them, hey, what is the smartest thing you've done in your career when it comes to routing policy? And in this slide deck, I'll try to give you an overview. We can talk for many hours about this topic, but I got 30 minutes, bear with me. In the presentation, I'll present you with a conceptual model and some associated terminology to make it easier to discuss the topic of routing policy, and I'll cover some routing policy design patterns that have proven to be successful in NTT's network and others, and I'll finally just provide some generic hints what to look out for when you're developing routing policy. So the conceptual model is if you have a few routers in a row, the orange router is mine, blue is NTT, and when I announce something to NTT over that eBGP session, the moment the BGP update leaves my router, it passes through a filter or a routing policy, which I would classify as the type eBGP out. And in Dutch, there's a famous saying, van dik hout zaagt men planken, which would translated mean one man's eBGP out is another man's eBGP in. So for every eBGP out, there is a corresponding eBGP in, but that's in a different administrative domain. NTT's router accepts my update, and it may or may not propagate the update further, but if it does, it leaves through iBGP out, and correspondingly, there will be an iBGP in. And I'll cover the function of each of these four types of filter. In your network, you may have policies that are actually called eBGP out, but I would recommend to not use those four words. They are types, not the actual names of the policies. If we take an iOS example, I chose iOS because this is readable to most of us. The blue encircled part is what I call an attachment point. This is where we associate a routing policy with a specific neighbor. And crucial to the attachment point is the directionality. Does this apply on stuff we receive or stuff we are sending? Then further down you see a route map. This is the actual policy, that total snippet. But routing policies are always, or most often, broken down into terms. On Junos, the word term is actually part of the configuration syntax. On BERT, a term can be a complex multi-line function. On OpenBGPD, every single line is its own term. So when you talk about routing policy development, these terms can be useful. So let's stride through these four types of policy. eBGP in. What is it we actually want to accomplish with the routing policy we apply on the eBGP in attachment point? And I would say that conceptually there is three types of data relevant in that particular construct. There is raw input, what we receive from the neighbors. There is bad, which we never ever want to accept under any circumstances. And then there is the whitelist, which is something which is the list of potential announcements we want to accept. So it's only a subset, it's the intersection between raw input and the whitelist that we want to accept, except for the bad stuff. Now let's go through this step by step. Raw input in IETF speak is adjacent RIP in. On some implementations, this is by default enabled and visible. On some implementations, you will need to enable soft reconfiguration inbound always to have visibility into that raw input. And raw input can contain anything in any quantity. It is an unknown set of routes that is coming our way. And this is where we apply maximum prefix limits. Let's zoom in on maximum prefix limits for a sec. Maximum prefix limits are a design feature to ensure that when the network behaves in something in a way we did not expect, that rather than hoping for the best, we tear down a session to avoid, to ensure there is minimal harm to the network or the internet. So it's a bit like a valve control. And if you click on the study resource links, there's a lot of inspiration that we can take from mechanical engineering, from valves, from electricity lines, on why fail-safe mechanisms exist, even if the fail-safe mechanism does not understand what went wrong. This is what most of us conceptually expect when maximum prefix limits are referenced. On the x-axis, we have time from left to right, time progresses. In the lower left corner, we see a small green portion that is the valid amounts of route. That's the steady state. Now imagine that the eBGP partner somehow makes a typo. They apply the wrong configuration. It happens. They start leaking their full table. At some point, you hit the configured maximum prefix limit and the session is torn down. And even though from that moment on, there is a service disruption specific to that circuit, the total network on both sides is saved and protected from harm, because if the leak would persist, you'd draw in all kinds of traffic and maybe it aggravates the issue. So this is what we think happens. But this only happens if the maximum prefix limit is applied pre-policy, so in the adjacent RIP in. Let's take a look at what happens when it's applied post-policy, so after passing through the routing policy applied to that specific eBGP neighbor. From left to right, time progresses. More and more routes are announced, maybe up to a full table. The route filter kicks in. It has the blacklist of routes it will never accept. It has the whitelist of potential routes it may accept. And it could be that the maximum prefix limit is set so high, say 30,000, and the amount of routes that manage to, that are part of the leak but still manage to come through the imperfect filter is lower than that, that maximum prefix is not kicking in. NTT had this a couple of weeks ago in Brazil. The curator guys wrote a nice blog post where they said, oh, it's so great, you can see NTT did filters. But in my mind, I was like, well, yes, the filters worked perfect, but maximum prefix limits were not kicking in because the filters were of great quality. So for a period of 2 hours, we were still leaking 3,000 or 4,000 routes that were part of the leak. And this is unfortunate. Pre- and post-policy prefix limits have different functions. Pre-policy defends against memory exhaustion. If I announce 2 million routes to you, your router should not attempt to store 2 million routes. After a number of routes announcements, it should just tear down the session because I'm consuming too much of your adjacent RIP in memory. The second purpose of a pre-policy limit is to protect against route leaks. If you normally announce a few thousand routes and suddenly you're announcing hundreds of thousands of routes, whatever it is wrong. Post-policy limits also serve a purpose, because post-policy is what is considered to go into your FIP and to be distributed in your iBGP. So post-policy limits can help mitigate FIP exhaustion or RIP exhaustion concerns. Or, and you see this sometimes in the layer 3 VPN context, post-policy limits are used to enforce contractual agreements. For instance, maybe there can only be 100 routes in the layer 3 VPN. Post-policy limit would be one way to enforce that. So now let's look at the vendors out there. Anyone from Cisco in the room? Come see me after class. Use this table to match it against your own configurations to figure out whether you're actually doing the limits pre or post limit. I was not aware for some of these platforms that accepted prefix limit was post policy, but that on Junos, prefix limit combined with keep none also becomes a post policy limit rather than a pre policy limit. I'm not expecting the vendors to improve the syntax or be able to clarify this better. That's why tables like these are handy. What I do hope, though, is that Cisco will consider a pre-policy prefix limit implementation, because this is needed in internet operations. We cannot adequately protect ourselves against leaks without this feature. Then another gap is outbound maximum prefix limits. For instance, NTT knows that if we announce more than 300,000 routes on our peering sessions, whatever it is, something is wrong. And we should proactively tear down the session and have engineering investigate why we are crossing the threshold which we expected. Many networks have only a handful of routes they will announce, like stop networks. It'd be ideal for stop networks that as a secondary control mechanism, they could just configure, I will never announce more than 100 routes, and if I do, something is wrong, tear down the session for our mutual protection. BERT, as far as I know, is the only BGP implementation that has a form of outbound maximum prefix limit, and I hope we can expand this to other vendors as well. But for that, we'll need to go to ITF and hammer out how this exactly works. But I think this will be a very beneficial feature in internet engineering. All right, now back to the triangle and the sweet spot of routes we do want to accept. The bad data set is simply composed of stuff like when there's bogan or private ASNs anywhere in the AS path, excuse me, whether there's bogan or private prefixes in the announcement, leaks. I've mentioned at a previous NANOG how our peer lock mechanism works, where we have a mechanism to ensure that we will not see level 3 behind Cogent and not see Cogent behind AT&T. This type of information is what we put in the bad section, and that will always be rejected outright. Others are IXP more specifics or RPKI invalid announcements. They go in the same category. And then finally, there is the whitelist. And this is something you should generate every 24 hours. You can use the IRR to generate the whitelist, or you can use additional resources like Aaron Whois, nic.br, RPKI, perhaps manually maintained whitelist in your customer database. But if you're a service provider and your business is selling transit, it is quite important that you provision the routers with a list you potentially expect behind the BGP session, and most certainly not just hope for the best. Cool, we got all that covered. Now what? Another famous European saying, when in doubt, use BGP communities. What is a community? And I must admit, personally, I think the word community was a terrible choice. As a non-native speaker, it has always confused me, like, why are we talking about groups of people when we're talking about a label on a BGP route? But apparently, grouping community was the best word at the time, so here we are, and we can never ever change it. Communities serve two purposes in the eBGP context. There's classification. So think geolocation. Where did I learn this route? From who did I learn this route? Was this a route from a peer or from an upstream provider or from a customer? There can be granularity involved, whether it was in Europe or specifically the Netherlands. RFC 8195 was an RFC written specific to large communities, but the same methodology applies to normal communities as well. And it might be an enjoyable read to further understand the differentiation between classification and the execution step. What is execution? Execution means acting when you see a certain BGP community. So that could mean do announce, or not announce, or prepend, or whatever you come up with. So let's walk through an announcement in this conceptual model. I have my ASN, I have a prefix that I announce to my upstream provider, and the routing policy at the eBGP-in attachment point will not reject the announcement because it's not a bogan and it's part of the whitelist. So it wasn't matching in the bad, it did match in the whitelist, so it can pass through. Then still in the eBGP-in policy, we'll run through additional things like features, local pref modification, or METs or whatnot. In the same eBGP-in policy, we also apply the classification. So NTT's policy will classify who this route came from and in what region of the world. And after that, it can pass to other routers. So it will leave through iBGP out and then go through iBGP in. And I'm skipping over iBGP out because out of the classes of policy, it's the most boring one. On iBGP in, however, there's all kinds of cool stuff that you can execute, like selective blackholing is where this is done. Or if it's a regional customer, that is the place to prevent routes from other regions to pass through. It passes through iBGP in, goes into eBGP out, and that's where you, again, have opportunity to apply features, mostly traffic engineering features such as prepending. Let's look at classifier execution matrix purely from a pass perspective, whether or not the route will pass. I built a very simple table. This is a service provider that has a customer, a peer, and an upstream. So this means that there is inbound from customers, inbound from peers, inbound from upstreams, and vice versa, the outbound variants. So from customer to customer, the execution will be pass if it matches the community that represents customers. If it's to a peer, we'll pass. If it's to the upstream and it comes from a customer, so we match on the BGP community that says this is a customer route, okay, we announce that to our upstream. The noteworthy thing in this table is that if there is no classifier, in none of the scenarios, the route should ever leave the BGP domain. If there's no BGP community on the route, never ever send it over an eBGP session. Rejecting routes without communities in the eBGP out routing policies is an incredible safety device. Imagine you're in a very large organization, one of your colleagues on another continent kind of experiments in the production network and accidentally hooks up, I don't know, a DDoS scrubber that announces routes. And for some reason, he forgot to apply any sanity policy on that BGP session. On some implementations, anything you learn on eBGP will be distributed to anything over eBGP. So while it's not ideal that the colleague attached this device and introduced routes into your BGP domain, the issue will be aggravated if you distribute these routes to your peering partners, upstreams, and other customers. It's about fault isolation. It's okay if faults stay constrained within specific domains. And one way of accomplishing that is never propagate routes if there is no BGP community that specifically allows the route to propagate through the filter. And the worst way of configuring a eBGP out policy is by doing the prefix matching, which routes you want to propagate to your neighbors at that point in the network topology. Because if you don't use communities, but you use prefix lists, you'll easily end up in a situation where if your customer leaves you and switches to another provider, that at that point, you'll learn the route via transit and then propagate it to your peers and other upstreams because you never qualified the relation using BGP communities. So as a bonus, if you use BGP communities, it also reduces the amount of work. You only need to change policy when you provision a new customer on one point in the network rather than update every PE. So I cannot stress this enough. Reject routes without communities. And if you fear this this type of control mechanism can impact your business operations, think of it this way. If you provision a circuit and it doesn't immediately work as you thought it would work, for instance, the routes are not propagating to your eBGP neighbors, that's a problem within the provisioning process where there's far more tolerance than later on, after provisioning succeeded, and the customer expects full service. Even worse, you can create outages that route leaks are costly, let's put it that way. All right, other hints when it comes to routing policy. Avoid regular expressions where possible. Always do direct matches where you input the real value of the community you want to match on. I mean, if we look at this example, is this some occult curse or a regular expression in routing policy? Who knows? And regular expressions don't make for readable code. The intention of a regular expression is extremely hard to decipher by coworkers that follow in your footstep when you either get promoted or leave the company. So write routing policy for readability, and that excludes regular expressions. Use separate policies for v4 BGP sessions and v6 BGP sessions. Don't try to be clever. Don't mix the APIs. Don't run v4 over v6 BGP sessions or v6 over v4. If you do this within your iBGP domain, you could argue that it's nice to use a single transport because it's a single administrative domain. But when it comes to eBGP, when it comes to debugging, consistency between the various vendors, I mean, who has formally defined what it means that if you have a v4 prefix list and you apply it on a v6 policy segment, what happens? Is that deny all or is it allow all? It's hard to say. So just keep the two internets separate from each other, like warm mayonnaise and Jägermeister. Don't mix it. Another hint I wanted to give you to see if you're on the correct trajectory when it comes to the design of your routing policies is just by looking at the amount of unique routing policies present in your total network. For each eBGP peer, I would expect you to have a separate eBGP in policy. You need separate policies because for each peer or customer, you need a unique whitelist. And that uniqueness makes it a separate policy compared to other components. But on the flip side, you often see that eBGP out can be shared amongst multiple eBGP neighbors, because at that point you're grouping. So NTT has per eBGP neighbor a unique policy on the inbound direction, but for the whole group of customers attached to that PE, there's a single routing policy for the outbound direction. Then iBGP out is often the same snippet across the entire network. You just copy-paste from router to router to router. But iBGP in often is unique per device, because each device is in its own unique geolocation, has, for things like selective blackholing, unique iBGP ins per device. To put that in numbers, eBGP in, we have tens of thousands in the network. eBGP out in the high hundreds, iBGP in low hundreds, because it's a unique policy per device, and then iBGP out, there is just one. Another thing we should be aware of is that the semantics of set community X differ from vendor to vendor. On some vendors, set community X will wipe out all the communities that are on the route, and then set that one community you wanted to set. On some implementations, some of the communities are deleted, but not all, and then it adds the community you wanted to set. Or there are implementations where set community actually is add community, but they use the word set community. What I advocate, because of this inconsistency across the vendors, and I'm talking the big vendors, so everybody is affected by this design pattern. Instead, use delete community, where you explicitly delete everything you don't want, and then add community. And the nice thing about this approach is that it makes it much easier to implement features like graceful shutdown. When NTT implemented graceful shutdown, we went from tens of thousands of instances of set community X to just a few hundred in a few corner cases, because we didn't want to wipe out the graceful shutdown community, but would want to leave it attached to the route so we can propagate it for others' benefit. So set community X should die. We should use different ways of expressing the desired behavior. And in the IETF Grow working group, we're actually trying to figure out how to properly document this inconsistency that grew over time and help operators understand what the device is doing. Another question I often see is, what communities should we delete? And I would advocate delete as few communities as you can. Because maybe those communities on a route are not of interest to you, but they could be of interest to downstream parties, partners, customers. So if you delete as less as possible, you may be benefiting someone else. Just delete what would affect your own network operations. We don't allow our settlement-free peering partners to announce black hole routes to us, so we delete the black hole route from such announcements. And this may be the only place where regular expressions are acceptable. Only exception. What communities to send to others? Just like I ask that you're conservative in what you delete when you receive routes, I ask that you're conservative in what you send to others. As a rule of thumb, I would advocate that you do not send more than 4 communities per route that you set yourself. And out of the set of communities that is useful to propagate, I would argue geolocation by far is the most useful community to inform others about. And be sure to publicly document what communities mean in your network. My final slide related to robust routing policies. I want to draw attention to RFC 8212. It specifies what BGP speakers should do on eBGP sessions. This was not formally defined. Some implementations would happily accept any routes and announce all routes they know when no policy is configured. And this, of course, has repeatedly led all of us into embarrassing situations. iOS. Then there are other implementations that, for instance, would accept everything but not announce anything. Or there's iOS XR, which does not propagate or accept any routes if there's no explicitly configured policy. And to address this inconsistency, we formulated an RFC that updated the BGP4 core specification. So this means that if your vendor does not support this RFC, technically speaking, they are not BGP4 compliant. Use that in your RFPs to get discounts. So iOS XR, BERT, and OpenBGPD are compliant. Great news. This is relatively recent developments. On Arista, you can emulate the behavior by typing in those commands. I wish they would make it slightly easier, or even better, do this by default. On Juniper Junos, you can emulate the behavior by using a Slack script that Adam Chappell wrote. Just go to the GitHub URL, load the Slack script into your Junos routers, and you'll have safer behavior. Of course, I'd like Junos to do this by default. Hopefully that will happen at some later point. Finally, Nokia, the Alcatel-Lucent brand, not the wireless skills, they committed to implement compliance with the RFC in 2019-2020 timeframe. So put some pressure on your vendors, send them a link to this RFC and ask them what's up. Now, this is the end of my presentation. If you have any questions, comments, please come to the mic, or you can email me.
Hi, Matt Petak, Oath, great presentation. eBGP in, you're seriously talking about doing a separate prefix list for every peer you have?
Do you define peer? as in eBGP neighbor, or peer as in settlement free?
Well, on your slide, you didn't explicitly call that out one way or the other. You just said, so is that actually, would you recommend that people build prefix lists for every peer they have, or just customers where you actually have the relationship?
I would recommend, oh, I see my boss wants to talk. I'll shut up.
So just to answer from practical experience, we at one point actually experimented with doing unique policy for every peer, meaning not just customers, but all peer, all BGP peers that we had in our network. The unfortunate discovery that we made is that at any given point, the hardware that's the volume, both the configs and any of the routing changes. So in our case today, as much as we would like to do that for everyone, we just limit that to customers. Job has presented
one
in
caveat. I know the network better than he does. Advocate, do the prefix whitelisting where you can. So on the really big peering partners, this is a challenge because they may not properly document what they potentially announce or whatnot. But still, if you consider things like peer lock, they make for unique policies per and vice versa. So even if the whitelist is not what you would like it to be, an extensive bad component can still yield very good results. And not all your peering partners are of the same size. If it's just a few hundred routes, it's entirely feasible to have per peer prefix limits. If we look at recent route leak incidents, many of them facilitated by a certain network, they extend incredible amounts of trust to very, very small peering partners, and this goes off the grid. So do this where you can, and there's only very few exceptions where it's not feasible.
Awesome. Thank you. We're going to cut the mic at these guys, so come on.
I was just going to ask, this is Don Smith, CenturyLink, sorry. I was going to ask and suggest that we start doing next prefixes like we do high and low mark. So once you go over the high, you alarm, red. You get back down to low, you go back to green. But you do cut it off when you get to max. So high and low would be like N% and P% or something like that would be your two high and low watermarks. Then you'd know, hey, this customer or this peer just got to 90% of the amount of route. Then when it drops back down to low, you take that glyph off the screen. It's just a suggestion.
To extend on that remark, when you configure maximum prefix limits, always configure a restart timer. Just let it repair in 15 minutes or so. That saves a lot of back and forth on the other side.
Julie Egerly, my network is a little smaller than yours. Actually, it's many small networks, but I do generate prefix list filters for every single peer. If you peer with us and you don't have an IRR object, you'll probably notice that we don't accept it. If you do have an object that covers all your customers, that's super helpful because those things are great. So the people who maintain those are really doing themselves a favor, and this is totally feasible if you have the good fortune to have enough memory, or in this case, something with a lighter memory footprint.
I've implemented per-peer prefix filtering using BERT in a hobby network. Well,
yeah.
I don't want to say your hobby network, but my hobby network.
Close enough. I mean, the way we experiment with it kind of feels that way sometimes. But like, it is definitely within reach that you can do this for every single peer on